Welcome to Brain Vision.
Okay, so this problem is all about friction and applying Newton's second law to calculate the static and kinetic coefficients of friction of a block of mass m on this horizontal surface. And I attach a light cord to it and pull with some tension T in this direction. So let's draw the free body diagram on the first and foremost, we'll draw that free body diagram on this block of mass m. So here's the tension. This is the weight downwards, right? mg, the normal force of the surface back on the mass, n, so that's equal to plus mg. And of course, before the block begins to slide, we have the static force of friction that opposes the motion, right? And we know in general the definition of static friction force is equal to the coefficient of static friction μs times the normal force. And since Fs is a force and the normal force is a force, that coefficient is dimensionless, right? So these things are newtons, dimensionless. Once the block begins to slide, this static force of friction will become a kinetic force of friction. And in general, static force of friction, the force needed to overcome that resistance to motion and initially slide, this is usually bigger. So μs is usually bigger than μk in general for given surfaces. So just keep that in mind. That can be a good check on our work. So the first part wants μs. So we're told that that threshold tension is 20 newtons when the block begins to slide. So we know 20 will be equal to μs times the normal force, which we know is equal to mg. We don't know the mass, but we can get that from the other piece of the problem because we're told we measured some data. Once the block begins to slide, we measured the acceleration in meters a second squared times the tension in newtons versus the tension in newtons, and we get a straight line, and we're told that the equation of that line is the slope 0.182 in some units. Actually, they're in meters per second squared Newton, which is actually just 1 over a kilogram. You should check the units as a check on your work, times T, right? Because that's our independent variable that we're varying and measuring, our dependent variable A, minus 2.842. So we measure that y-intercept, right? This has now the form of y, just a line, y equals, I'll use capital M, x plus b. So now we know the slope. Then, since this is in units of 1 over kilogram, m is equal to 1 over big M, the slope. So 1 over 0.182, you put that on your calculator, you should get 5.49 kilograms. So it's about 5.5 kilogram block. So now we can go back and solve for μs here, right? Then I'm going to bring that over here, right? Because 20 newtons is where that tension becomes large enough. So we have 20 over, I just solved for the mass, it's 5.5, times g, the acceleration due to gravity, which on Earth is 9.8 meters a second squared. So if you do this out, put it in your calculator, you should get μs is equal to 0.37. So that's your answer to part A. Part B asks for the coefficient of kinetic friction, right, which we can get from the y-intercept here. Because once the block is moving, we apply Newton's second law, which we know in general that the net force on an object, F net, which is a vector, is equal to the mass of the object, m, which we solved for, now we know it's 5.5, times the acceleration of vector, so the force in that direction. So the net force when the block begins moving is is T minus the kinetic force of friction, right? It opposes the motion. The motion is in the direction of the tension, equals ma. We can plug in what we know Fk is. It's mu k times the normal force, which we know is mg. So now we almost have the form that our line is in. We just have to divide both these sides by m. And I'll do that over here. And I'll put a on this side so it's easier to see. A is equal to, well, we don't need the vector sign. We'll just, a is equal to the form of that line, right? So T over M minus mu kg. So we're varying T, that's our X, and measuring A, that's our Y. So we already used the slope, so then B equals minus mu kg, and we know B is minus 2.842, so if you solve for mu k, minus 2.842 over negative 9.8, the negatives cancel, right? And since both those are an acceleration, we're given the units of B too. They're an acceleration, so we get, again, a dimensionless mu k, and you should get 0.29. So that's your answer to part B. And we did find, in general, mu s greater than mu k, since the static force of friction in general is greater than mu k for given surfaces. So now part C asks, if you were on the moon, how would this experiment change? How would that graph of your data on the moon, now if we slid the block on some horizontal surface, how would that change? Well, what changes is that acceleration due to gravity, g, meters a second squared. It's actually the gravitational field strength of the planet in units of acceleration. So g moon is less than g earth. But the physics is generally the same, right? Our free body diagram is the same. It's just that this strength changes. So that slope, since it was only dependent on the mass, which doesn't change no matter the planet you're on, it was over big M. So the slope is going to be unchanged. But since the y-intercept depends on g, it'll decrease. So slope unchanged. So you'll just get a shifted line. The slope's going to be the same, but it's going to be further down. So Earth experiment, if we label our data lines, the Earth one would be on top, the Moon one with the same slope, but just shifted down, since B decreases. And that's the problem.